Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Hi, so today we're going to go over a lot of fundamental organic chemistry problems. So this is more of an introduction for you to better understand this topic. And so the first part that I'm going to start out with is called molecular structure, the introduction to this, and a review. And so you guys must have seen a little bit of organic chemistry already by learning about general chemistry. But now we're going to delve into more complicated things further on in these videos. And so you guys should already know that organic chemistry is the study of compounds of carbon, and there's over 20 million organic compounds that have been identified. And basically in organic chemistry, we make things for various different applications, such as pharmaceuticals, fuels, paints and adhesives, cosmetics, we work with DNA and proteins, and all of these things can be made via chemical reactions. And so I just showed you guys this very general picture right here where various different aspects of science such as medicine, energy, products, catalysis, chemical biology, and environmental issues all stem from this fundamental topic. So in the introduction and review, I'm going to go over hydrocarbons, also naming, molecular formulas, and structural formulas, also going over some basic IUPAC rules just to remind you guys of what that is, also some substituent rules, and also we'll go over functional groups because that's a very important thing that you'll see more of when we delve into the more complex aspects of organic chemistry. So let's get started by talking about alkanes, alkenes, and alkynes, which are hydrocarbons. So I hope you guys remember learning about hydrocarbons in your general chemistry course. And basically what hydrocarbons are molecules that only contain carbon and hydrogen. And so that makes sense, right? Because it's a hydrocarbon. So there's three main families of hydrocarbons that we went over in general chemistry that I'm reviewing for you here. And I'm going to also include other concepts that I think will be very important for you guys to review and understand before we get into the more complex stuff. And so the first one is alkanes, which has the suffix -ane. And then we have alkenes with the suffix -ene. And then we finally have alkynes. So if you remember, alkanes consist of single bonds. And so when you just have one single bond, it's called saturated. And on the other hand, for alkenes, we have double bonds between the two carbons. And this is called unsaturated. So basically, when you have more than one single bond, the bond is called unsaturated. So for alkynes, we have a triple bond between the two carbons, and this is also unsaturated. So just a basic review of a single bond versus a double bond versus a triple bond. Remember, the single bonds are composed of one sigma bond. And then a double bond consists of one sigma and one pi bond. And finally, a triple bond has one sigma and two pi bonds. And so from here, we can also talk about what hybridization each of these different families have. And so in the case of a saturated alkane, it's usually sp3 hybridized. So in order to show you this, a good example of a saturated alkane is methane. And methane is the simplest hydrocarbon, which is CH4. So one carbon and four hydrogens. And so if I drew out methane for you, because I know how to draw VSEPR structures, it would end up like this. So again, another thing you might want to review is VSEPR, which is a fundamental general chemistry concept that you'll need to know to apply in drawing all the different molecular formulas that you'll see. And so in this case of methane, you have these carbon-hydrogen single bonds, and you get this tetrahedral structure. And since it's tetrahedral, all the bonds between all of these guys is 109.5 degrees, and it's sp3 hybridized. So now let's look at alkenes. Alkenes have a double bond, so they're sp2 hybridized. And a good example of this is ethene. And as you can see, methane ends with ane, ethene ends with ene. That tells us what family it belongs to. So ethene is C2H4. And if I drew it out for you, it would look like this. So as you can see, now this part, if you look at just one side of this molecule, is in a trigonal planar conformation, right? And so this is called trigonal planar, where the bond angles are 120 degrees, and that's why it's sp2 hybridized. Finally, let's move on to the alkynes. The alkynes are sp hybridized due to this triple bond. A good example of this is ethyne, where now it has the suffix of -ine, which tells us that it has a triple bond, and this can be drawn as C triple bonded to C, and then a hydrogen and a hydrogen. As you can see, the reason why all three structures look like this is because carbon always wants to have 4 bonds. So if it's single bonds, it has 4 bonds like so. If it's a double bond between the carbons, you have 1, 2, 3, 4. Finally, in this case, you have 3 between the 2 carbons, then 1 with the hydrogen. So in this case, we end up with a linear structure with bond angles of 180 degrees. So as you can see, by seeing how many bonds each of the different molecular structures you see have, you can basically put them in the different families of hydrocarbons, whether they're alkanes, alkenes, or alkynes. Also, the general formula of identifying each of these different hydrocarbons is for alkanes, it's CnH2n plus 2. For alkenes, it's CnH2n. And then for alkynes, it's CnH2n minus 2. So I can show you how this works. In the case of methane, it's CH4. That means it's C1, where n equals 1. And so 2 times 1 is 2, plus 2 is 4. So it would be C1H4, so CH4. For ethene, we have C2H4, so n equals 2, 2 times 2 is 4. Finally, for the ethine, we have C2, and then 2 times 2 is 4, minus 2 is 2. So C2H2, which is what we have like so. So I also wanted to show you guys this table just to remind you of all of the different prefixes we use for the hydrocarbon names. And so when we just have one carbon, in this case we have methane, where the prefix is the meth. When we have 2 carbons, we have eth for ethane. When we have 3 carbons, we have prop. For 4 carbons, we have bute. For 5 carbons, we have pent, and then hex, hept, oct, non, and then dec for 6, 7, 8, 9, and 10 carbons. So this is an example for when you have an alkane. So these are all single bonds since all of the suffixes ends in ane. But if you had, for example, a 3 carbon but with a double bonded structure, it would just be called propene. If you have 5 carbons, but then you have a triple bond within the structure, it would be called pentyne. So basically by using all of these prefixes and then combining that with the suffix based upon whether you have an alkane, an alkene, or an alkyne, you can create any structure and name it by using this table. And also one thing that's really useful about this particular table is it shows you the condensed structural formula. So as you can see, CH4 can be written as just CH4, but then when you have C2H6, instead of drawing it out like this, you can write it out in a condensed form, which just involves CH3 right here, and then CH3 right here, and thus it's CH3CH3. When you have C3H8, it now looks like this. 1, 2, 3, 4, 5, 6, 7, 8. So when you write out the condensed structural formula, you have CH3, but then a CH2 in the middle, and then a CH3, which is this structural formula. So this is a really good thing to just review to make sure you know how to name all the different hydrocarbons.